Welcome back. Let's now talk about TD3, which is also part of the actor-critic family. As a reminder, don't forget to enroll in my free Udemy tutorial, Vehicle Suspension Control 4, PID Tuning with AI, TD3. You will get the code files and video explanations if you enroll in that tutorial. Also, note that the free coupons that I offer for that, they have limitations in terms of time and the number of enrollments. However, don't worry, I will be renewing them periodically. We left off with DTPG, Deep Deterministic Policy Gradient. I explained to you why we needed extra two neural networks, target actor and target critic, in order to have a more stable learning process. However, experiments have shown that in DTPG, the critic tends to overestimate the Q values for the given state-action pairs, leading the agent to make decisions which are not optimal. To fix this problem, the following modifications were done. You again have your regular actor, which takes in the state vector. It outputs some action, to which we add a little bit of noise. That will give you a noisy action. The environment takes it in. Your states are also your observations. But now, instead of one critic, you will have two of them. This is critic 1 and this is critic 2. Both of them take in the states and the noisy actions, and both of them output two Q values, which are the current Q values. And just like in DTPG, you have a target actor, and for each critic, you also have a target critic, which means that in total, in TD3, you have 6 neural networks. And just like in DTPG, before you update your current Q values, when you apply your noisy action to the environment, you first figure out the next state, which goes into the target actor, and then it also goes into the first target critic and into the second target critic. And now the target actor will give you an action vector at k plus 1 due to the state at k plus 1. And now we do add a little bit of noise to the action vector here as well. In TD3, you add noise here and also here. And then this noisy action vector also enters into the two target critics. Both of them will then give you two Q values, Q1t and Q2t, for the given state action pairs. And now, remember that the problem with DTPG was that the critic was overestimating the Q value. To combat that, in TD3, you would compare these two target Q values that you can see here, and you would take their minimum. That helps the algorithm reduce the overestimation of the Q values by the critics. This QT min is then multiplied by the discount factor. That will give you this term. Also, when you applied this action to the environment, you would receive an immediate reward for this state action pair. You would add these two terms together. That will give you these two terms. And then you would subtract the current Q values from them, giving you two errors, which are this and this respectively, where plus and minus give you a minus, so you are subtracting Q1 and Q2. And then you use gradient descent to drive these two errors to zero by adjusting the weights of the two regular critics, critic 1 and critic 2. That's how you train them. And the reason why this configuration helps the algorithm fight overestimation of the Q values is because when you take the minimum of the Q values produced by the target critics, then you make this target Q value smaller. When you drive these errors to 0, you converge on the target Q value. And when you make the target Q value smaller, your current Q values will converge on something that is smaller. When it comes to training the actor, then you would again use gradient ascent, but you would only apply it to this first Q value. In other words, you would adjust the weights of this actor such that when a state vector comes in, the action that is chosen causes this current Q1 value to increase and ultimately be maximized. I would assume that you could also use regular critic 2 for that. However, based on my research, this Q1 is used to train the regular actor, and therefore I will do it too. The other thing that is different from DTPG is that the actor is updated less frequently compared to the critics. Based on my research, regular actor is updated every second time the critics are updated. So the critics are updated here, here, and here on the time axis, but the actor is only updated here and here. All these changes, like noise addition, extra critics, taking the minimum, updating the regular critics more frequently compared to the regular actor, they were all added to TD3 in order to improve its performance compared to DTPG. One thing that I want to mention is that when you train your regular actor to take actions that increase the Q1 value, in that case, the action vector that comes out of the regular actor network is directly fed into the first critic. In that particular case, you do not add noise to it. The noise is added when you train your critics, but not when you train the actor. You will see that later in the code as well. Finally, just like before, the target actor and critics weights are updated much slower than the weights of the regular actor and critics in order to make it easier for the algorithm to drive these two errors to 0. Once the training is done, you take this trained actor and you deploy it. It will take in the states and output the 6 PID constants, which are your actions. What I have just explained to you is called twin delayed DTPG or simply TD3. And this is what I want to use in tuning PID controllers used in the half-car vehicle suspension system. This is the end of the theory section on YouTube. Thank you for watching. Make sure to enroll in the free Udemy tutorial to get the code and the explanations. Thank you.